Well, this section 3.7 is about rates of change in the natural and social sciences. And all of these things, velocity, density, current, power, all of these things are dealing with a rate of change of some kind. And a rate of change, just like the change in y over the change in x, is a derivative. All of these are in some way a derivative. We're finally kind of getting to the place where the calculus is and the math is real world kinds of stuff. Marginal cost, for example, is the rate of change of the cost function, marginal profit. If you take a calculus course, if you major in business, you'll definitely take a calculus course for business majors, and that's one of the topics you'll talk about. One of the main things that we're going to deal with in here is the derivative of and thus the rate of change of the position function. So if you have some equation that defines what your position is, then a change in your position is the velocity. And after that, the change in velocity is acceleration. So there's a relationship between these three things. If S of t defines your position, I don't know why they use S, they just always seem to. If you take S of t to be your position, then the derivative of S would be velocity, and the second derivative of S would be your acceleration. And then likewise, the derivative of velocity would be acceleration as well. And so we're going to use that idea in this section. And one of the main kinds of problems that we're going to use or do out of this section, I'm just going to do one out of the homework. But the key element of this section is to be able to recognize any of the environments in which you could apply a derivative. Because on the AP exam, they're going to have some problems and some things that I haven't thought about presenting to you, and you got to go, oh, they're talking about a rate of change, that's just the derivative. So let me show you this problem and help you understand how it works. This is actually just straight out of the book on page 179, so if you want to follow in there, that's fine. The reason I did that is because there's a whole bunch of questions that they ask. This for problem number one, there's A through I, and each of them kind of leads you down the path of understanding on this. So let's go through this and see what happens. So I'm going to take a function, and this is actually number 2, as I said back here. Number 2 out of the homework. So this function is defining a position of some molecule or some object. Now you can think of that position as being just describing it as back and forth on the number line. Now notice if you take f of 0, if you put 0 into there, you get 0. So at time 0, this object is at 0. As time progresses, this function will define where the object is, whether it's to the right or whether it's to the left or where it is on this thing. And what you often see in this kind of a problem is that when you have an object where it's being defined by a motion, it might start off going this way, stop, and then turn around and come back this way, and then stop and come back, and it might do some zigging and zagging depending upon whether you get positive or negative answers for that. So first question says just find the velocity at time t. So the velocity of an object is simply the derivative of the position function. So I take the position function and take its derivative, and that's what you get. Simple as that. Part B says to find the velocity after 3 seconds. So in other words, plug in 3 into the equation. So as it turns out, when you plug 3 into this, that becomes equal to 0. Not always the case, but in this case it is. Part C says when is the particle at rest? So if I want to know when the velocity is equal to 0. Now we already found out that t equals 0. When t equals 3, that the velocity is 0. But you see that by taking this equation, setting it equal to 0, factoring out the common factor, which leaves behind t minus 3. And so when you set both of these equal to 0, you get t equals 0 and t equals 3. So at time 0 and at time 3, this object is not moving. It's coming to a rest. Part D says, when is the particle moving in a positive direction? So now at 0 and at 3, I know that the object's not moving. So what I want to do is test on either side of 0 and 3 and find out if the velocity is positive or negative. What I'm looking for, here's the velocity function, here it is factored. I want to know where it's greater than or equal to 0. So I got the two places where it's equal to 0, and I can just find that by testing some points. Now, if you remember some things from last year, this graph is a, nope, not that one, sorry. This graph right here is a cubic, and cubics tend to do something like this. But notice that this 0 happens twice. It's a squared, and what that means is the graph doesn't cross the x-axis at 0, it's just going to touch it. So the graph of this thing looks something like this. It's going to come up, touch at 0, and then touch and cross at 3. So you can verify this by actually plugging numbers into the velocity function. If you plug in a negative number, this will be negative. If you plug in a number somewhere between 0 and 3, this will be also negative. But if you plug in a number greater than 3, this will become positive. And the graph looks like this. And the reason we spent all that time last year thinking about how graphs look and their shapes is so you could just intuitively understand, because this is t squared, it's just touching the x-axis, not crossing. So the question was, when is the particle moving in a positive direction? Well, only for values 3 and above. Notice the 3 is not included with the parenthesis here because you can't, it's not moving at 3. Then part E says, find the total distance traveled. Now, you got to understand something. And it says in the first 8 seconds. So this thing's moving from time 0 to 3. Remember at time 0, the particle was at 0. But for the first 3 seconds, this object's moving backwards. And then at 3 seconds, it stops, and it turns around, and it starts going forwards again. So if I want to figure out how far I've traveled, I'm going to make up some numbers real quickly just to kind of help you understand. Let's say this is down to -7, and up here is 5. So how far did this object travel? Well, it started at 0 and ended at 5, but it traveled more than 5 because it went from 0 to 7, it went 7 units. And then from 7 to 5, it went 12 units. So total, this object would have traveled 19 units. Now, the way you get that is you find the distance between these two, and you need to take an absolute value of that. That's what's going on there. You're going to then find the distance from here to here, and the way you find distance between 2 points, by the way, is subtraction. The distance from 5 to -7 is 5 minus -7. That's how I got 12, plus the original 7 going down. That's where the 19 comes from. So I'm going to take and find my position at time 3 and subtract my position at time 0. Now I know to use 3 because 3 is where it stops and turns around. Well, as it turns out, these were just totally made up numbers down here. It only got down as far as -0.27. So the distance it traveled from time 0 to time 3 was 0.27 units. Then I need to take a look at where it traveled from 3 to 8. And so find out its position. Notice this is S, the position function. And so find out the difference in its position from 3 seconds to 8 seconds. That was 20.75. And I'm getting those numbers just by plugging it into the original equation. You can do that on the calculator real easily. And then you just need to add those two things up, and that's the total distance that it traveled. Part F asks you to draw a diagram to illustrate the motion of the particle. So it looks something kind of like this. Now, this particle you could think of it as just moving back and forth on the x-axis, but you couldn't see that very well. And so we do it kind of two-dimensionally, even though it's really just moving back and forth. So at time 0, it was at 0. At time 3 seconds, that's the moment when it stops and turns and comes back, I'm at -0.27. And then at time 8, I end up here at 20.48. And that's just simply a simple graph of how this object is moving during those first 8 seconds. Starts off going in the negative direction, stops, turns around, comes back, and goes this way. It's hard to see when they overlap like that. That's why you do it as kind of a curve to show that it changed directions. So here's another problem. I think out of the book as well. I'm going to run through the same logic. Sorry. So in this case, I lost track. This is problem G, part G. Thanks. We're looking for the velocity now. I was thinking it was a different problem because that was the velocity there, not the original equation. So to find in part G, to find the acceleration at a certain time, I need to take the derivative of the velocity function. So multiply the 3 down, multiply the 2 down, they get smaller by 1. And then it says find the velocity at time 3. So I plug 3 into the equation and just do the computation. Now acceleration is in feet per second squared. And then the problem is defined at this case is seconds and feet. So it's feet per second squared. They then, in part I, say when is the particle speeding up and when is it slowing down? Now, you have to understand something about how the physics works here. If I take something and I throw it up into the air, it has positive velocity because it's going up. But the acceleration it's experiencing is negative because of gravity. So if you have positive velocity but negative acceleration, it's slowing down. And think about it, when you toss something up in the air, it goes up slower and slower and slower and slower and slower. And it finally gets to the peak, right? And the velocity becomes 0, but then the velocity becomes negative. Now gravity hasn't changed, it's still negative. But now what's happening to the particle is, or the ball or whatever it is, as it's coming down, it has negative velocity, but it also has negative acceleration. And so when the signs of these two things are the same, then the object is speeding up. Thanks. So as it speeds up, coming to the ground, it goes faster and faster and faster. The position of the particle doesn't affect whether it's speeding up or slowing down. What it matters is whether these have the same or different signs. If the acceleration and the velocity have the same sign, it's speeding up. If they have different signs, then it's slowing down. So here's what I know about the velocity, right? From 0 to 3 seconds, the velocity was negative, and from 3 to 8 seconds, the velocity was positive. Let me now compare that to what's going on with the acceleration. So I took the acceleration equation, and I found out where it equals 0, and I know it's equal to 0. I find it's equal to 0 at time 0 and at time 2. So I'm going to compare all of these regions and see what's going on. So between 0 and 2, both of them have negative, and by them I mean the velocity and the acceleration, both of them have negative values. So from 0 to 2 seconds, the object is slowing down. Said it backwards. The object is speeding up. From when I go to the next one now, from 2 seconds to 3 seconds, the velocity is still negative, but now the acceleration is positive. So in this case, this is negative, this is positive. Now it's slowing down when they're in opposite directions. After 3 seconds, though, this is positive and this is positive, and so now it starts to speed up again. And so think about how this works. As you started off, it had negative velocity. It was going faster and faster and faster. But then at 2 seconds, it starts to still go negative, but it starts slowing down because it's going to have to stop. And then it stops at 3 seconds. Now it starts turning around, and notice what happened in this case. I still had at 3 seconds, right? Now I change from, here's where 2 was, and it starts slowing down because it has to stop. But it's accelerating that way, and so now I started moving in the direction I'm accelerating, so it just keeps going faster and faster that way. So then the last part of that question is, so I'm speeding up from 0 to 2, I'm slowing down from 2 to 3, and then speeding up again from 3 to 8. And again, all you're looking at is where are these the same and where are they different. I think that will give you a pretty good feel. I'm not going to go through the next example. It's another one out of the book. But I think this gives you enough of a feeling of how to work through that you'll be able to figure it out from there. We'll talk about this more in class later.